turn your attention to the list of sponsors that we're having on the screen. Our signature sponsor this year is Dr. Darren Holt. I would also like to thank our gold, silver, and bronze sponsors. And your contributions go much farther than simply putting on today's event. The proceeds directly support scholarships and fund many enhancement programs for civil and structural engineering students at NC State. And perhaps most significantly, the inspiration that students receive from attending this event each year. Please see the program for today's on the screen. During any time, you can ask questions in the Q&A box. We will moderate the questions and share them with the speakers near the end of the lecture. 2 PDHs are available for attending today's event, either here or virtually. We will send out all PDHs via email within the next couple of weeks. At this time, I would like to introduce Dr. Luis Martin Vega, Dean of NC State College of Engineering. Dr. Martin Vega.
Thank you very much, Santiago. On behalf of our College of Engineering, let me also extend a welcome to everybody here and everybody who's online. I want everybody to understand that everything we do in life is really on the shoulders of those who came before us. And oftentimes, or not oftentimes, sometimes you have the pleasure and the good luck to have the shoulders in front of you be that of a true giant. And that is what Dr. Paul Zia is. What he has meant, not only to the Department of Civil Engineering, to the College of Engineering, to NC State, is something that you really can't describe in words. This is the 21st Paul Zia lecture. I remember when it was the 5th or the 6th. And I have to tell you that it has really grown beyond anything that people might have thought of that moment. Although I think those of us that knew Paul felt that we're not surprised at all by everything that's happened here. So Paul, we all owe you a tremendous debt of gratitude. It is tremendous honor and privilege to be here. And I know we're going to hear from him in a minute, but please join me in a tremendous round of applause for Dr. Paul Zia. Thank you. As some of you may be aware, Dr. Mort Barlaz, who was the head of the Civil Engineering Department for over 11 years, stepped down last year. He did a tremendous job in his role for many, many years. And we were very fortunate to be able to attract and bring to civil engineering its new department head, and I'm referring to Dr. Jackie McDonald Gibson. And Jackie comes to us from the University of Indiana, where she was most recently department head of the Department of Environmental Engineering. But a lot of her background is with the program in environmental engineering at UNC Chapel Hill. Her graduate degrees are both in civil engineering and in environmental, I think it's engineering and public policy from Carnegie Mellon, which is really a unique combination. But the bottom line is that we're delighted to have her here. And I want you to join me in giving her a very warm welcome, as this is her first Zia lecture, and it certainly won't be the last. So Jackie, if I could ask you to come forward.
Well, thanks so much for that warm welcome. I have to say I'm truly humbled to be following in the footsteps of Dr. Zia and Dr. Barlaz and Dr. George List, who is another chair. In between, you leave a tremendous legacy, and I'm going to start really lifting weights so I can try to leave strong shoulders for the next person, but I think it's going to take some doing. So it's really wonderful to see all these people here in person. And I'm, of course, really glad people are able to participate online as well. But what a wonderful thing to see this group of engineers, architects, contractors, students, faculty, and other members of our community come together to honor Dr. Zia. And of course, Dr. Zia is such an incredible example of how research in civil engineering can actually really make people's lives better. You know, he's elected to the National Academy of Engineering, which is really the highest honor that an engineer can achieve based on research in this country. And his work has led to safer structures for all of us. And so again, I'm truly honored to be here, and welcome to you all. What's really special about this lecture is not only that it honors Dr. Zia, but it also really is a wonderful opportunity to link our students to the real world of engineering and give them a chance to really see how what they learn here can really translate to doing really big things, and even to introduce the public and the broader community here about the great work that can come from civil construction and environmental engineering. We've had lectures, previous lectures, representing some of the most exciting infrastructure projects all around the world, from Australia to Dubai to Greece and all corners of the United States. And finally, I just want to again echo Santiago for thanking the sponsors. An event like this requires substantial contributions. So thank you so much to our presenting sponsor, Dr. Holt, and to all of our sponsors, gold, silver, and bronze, shown on the program for making this possible. With that, I will turn the mic back over to Santiago to introduce Dr. Zia.
Thank you, Dr. Gibson. At this time, I would like to present a video presentation, video introduction to Dr. Zia, which should be on this slide. Brandon, I don't know if you can play the video.
Good afternoon. It is my great pleasure to extend a warm welcome to all of you who are here attending the lecture in person, and to many others who are attending virtually. I'm impressed by the remarkable record that the lecture has been presented as an annual event for 21 years without interruption. The lectures have showcased some of the world's most critical infrastructure created by civil engineering professionals. They not only illustrate the creative and unique solutions of the project, but also demonstrate the economic, social, and cultural impact on the society. As in the past, this year's lecture will again feature a major urban renewal project in Seattle. Our speakers will share with us their innovative ideas of the design and construction of the project. The success of the lecture series would not have been possible without the support of many people. First and foremost, our special thanks to the speakers who take the time off from their busy schedule and come here to share their knowledge and expertise with us. Thanks also to the Program Planning Committee for their efforts and dedication. We are also very grateful, fortunate to have the steadfast support of Dean Martin Vega and Dr. Barlas and his successor as department head, Dr. Gibson, who joined us just a month ago. Above all, we must extend our deepest appreciation to the generosity of the sponsors. Their support is crucial to the success of the program. I was pleased to learn recently that the sponsors have raised a total of $450,000 since the beginning of the lecture series, and the program has attracted 65,000 registered attendees. The funds provided by the sponsors support not only the lectures, but also an endowment education fund in the department, which supports the special education needs of the student, such as travel expense to conference presenting papers, or for class field trips. The endowed fund also provides for one or more scholarships for outstanding academic achievement. It is my sincere hope that the lecture series will continue to flourish for the years to come. Again, thank you all for coming.
Thank you very much, Dr. Zia. At this time, I would like to welcome our speakers, Mr. Ron Klemenczyk at MKA in Seattle, Washington, and Dr. Varma at Purdue University.
Great. Hello. Hi, everybody. Good afternoon, Wolfpack. This is my first visit to NC State. It's proved to be better than I imagined. The hospitality and warmth that I've felt the last 24 hours is spectacular. Really honored to be here. Dr. Varma and I are both very honored and delighted to be here in this really prestigious lecture. In particular, with Dr. Zia here, it's only a little intimidating to have him in the front row. True legend in structural engineering, someone that I've only read about until just yesterday. I always held him in the highest regard for his work and was an inspiration to me in my career and many others. So really honored and delighted to be here. Today we're going to talk about a project, but we're going to talk about much more than just a project. Really about a collaboration between practice and the research community and how we can make structural engineering better, how we can innovate, how we can build new things differently, faster, better, safer. And that's really the story we're going to share with you today. It's not so much about the building, that's just the frame in which the picture is presented. So we're going to share some of the details of the building, but I want you to reflect on the story behind it. And the story behind it really is this collaboration that started almost 15 years ago, and it continues to this day. So we're going to talk about this building, and we're going to tell you what it is, and then we're going to tell you a little bit about why we did what we did, what launched us on our journey, and then we're going to get into the details of how we did it. And I think that maybe is the more fascinating part of all of this story, is the how we went from doing something that might have been ordinary every day, yeah, we did it in the last 30 projects that way, to something that's never been done before. A whole new structural system, a whole new way to assemble a building. And that's, again, the story of this building. So if you'll bear with me for 1 second, I'm going to do something just for my own personal comfort. I'm going to get a little casual here, and we're going to get down to business. All right, I feel better now already. All right, so the team, right, we can't do these projects without a client. And in this case, Wright Runstead is a developer in Seattle. Wright Runstead we've worked with for about 30 years. And why I really want to highlight them is we can't do these things without somebody who's willing to take a chance on us, willing to have the confidence and trust in our capabilities. And fortunately for us, this is not the first time Wright Runstead had been to that rodeo. The very first performance-based seismic design building done in the United States, we designed for Wright Runstead in the mid-1990s. So they'd been to this dance with us before, and they knew what it was going to take to do something adventuresome. The building itself is very large. In Seattle, it's the second tallest building in Seattle. It's a mixed-use building. It has apartments on the top, office for 2/3 of the height, some little bit of retail in the base, and then 1,000 cars below grade, a huge, huge parking garage. We could do a whole seminar by itself on the below grade construction. Today, we're going to focus on the above grade construction, which is the Speed Core project itself that we came to talk about. How the building's organized is much like any other office building is organized. Here you see a low-rise, a typical low-rise floor plan, where the red color is the core of the building, the structural backbone that braces the building against wind and seismic loads. Let's see, we're going to talk about feet or meters here. Let's talk feet, I guess. All right, so the core itself is about 40 feet wide, and each of those red boxes you see is 40 by 30, and there's 3 of them, so 40 by 90 in its totality at the base of the building, and it houses the elevators, the stairwells, the toilet rooms, what have you. As the building gets taller, the floor plate shrinks. And with that floor plate shrinking, so shrinks the core. And so on and so forth to the top of the building, where we're left with a singular concrete box that's 40 feet wide and 30 feet long. And this is how the building was to stack, apartments on the top and office below. That core by itself at 850 feet tall wasn't going to be stiff enough to brace the building. So in addition to the core, we introduced a series of outrigger trusses and belt trusses that were located about 2/3 of the way up the building, just at the intersection of where the office stops and the residential apartments begin, at some mechanical floors, if you will. That was a convenient place to put these outrigger trusses. And how the outrigger trusses work, kind of the analogy I like to use, is like the ski poles for a skier. If you're a skier and you're going down the mountain and you have no poles, you can make your way down, but it's a pretty wobbly ride. And if you put the ski poles out there, you feel a lot more balanced and you feel like you have a lot more stability. That's what these outrigger trusses and the columns that support them do. It adds a lot of stability to the building. So that was the basic geometry of the building. How buildings have been built for the last 30 years in many, many places all around the world is using a reinforced concrete core surrounded by steel floor framing. There's a long history as to why that is. We don't have enough time for that story today, but for the most of my career, for the last 30 years, this is how we've been building high-rise buildings. Concrete core, steel floor framing. What's unique about this picture, if you look at it closely, you'll see, wow, the concrete core is being built way out ahead of where the steel erection is occurring. That was the fundamental question of this project, because that time lag, and the reason because there is a time lag is because the concrete formwork cycling and the construction of the core can proceed at about 1 floor per week. That's about as fast as you can build it. The steel erection, on the other hand, can go 2 or 3 floors a week, much, much faster. So there's this lag in the start time between when the steel begins erection and how far ahead the concrete needs to be. This was the question that we asked ourselves, was how do we address this and make the building go faster, squeeze that time lag out of the system with some other approach to building the building and allow us to save several months on the schedule. Confounding kind of that concrete ahead was this connection between these trusses and that concrete core. And if you think about how to connect these very large steel trusses back to a reinforced concrete core, through the core, across the core, and then to the trusses on the other side, the amount of embedded steel that would need to go into that reinforced concrete wall is substantial. And the amount of time required and the complexity of assembling all that on site was substantial, again, kind of confounding the construction process. So that's where we had this idea. And the idea was a composite plate shear wall system that was concrete filled. This is before we had this name SpeedCore. Actually, we borrowed this idea. We borrowed it. We didn't really invent the technology. We borrowed the idea from a group that originally came up with a product in the UK called Bi-Steel. It was a similar idea with 2 steel plates interconnected by some rods or tie bars and then filled with concrete. That particular assembly was proving to be very useful and very robust as it related to blast, impact, and all kinds of other loading conditions, but no one had ever thought about it for a high-rise building. And that's what was intriguing to us. How can we adapt this technology to a high-rise building? The basic assembly you see here in plan, right? There's a steel plate, and they're interconnected by these tie rods. And how you go about making that becomes really important because there's many, many, many pieces involved here, but the process was to do that all in a prefabrication plant. Modularize it, prefabricate it, and then erect it in the field as you would stacking Lego blocks. Maybe we'll come back to that. The panels themselves, as we imagined, were 1 story tall and 1 bay long. So in this case, 14 feet tall and 30 or 40 feet long, such that you could prefabricate them, you could put them on a truck and ship them to the site, pick them up with the crane and set them in place. Some of the other panels in the building needed doorways in them. And so we thought about, well, how might we imagine creating the panels with the doorways? And this was what we came up with, was this dog bone shaped or H-shaped panel that incorporated a link beam, which as structural engineers were very concerned about how the link beam is constructed, how it will perform, and its contribution to the overall system. And we wanted to control that very tightly, but how all that geometry came together was very important. And then finally, how are we going to connect these pieces together in the field? How would we splice one panel to the next panel? Lots and lots of thinking that went into all of these kind of basic ideas. About the time we were hatching this idea, Engineering News Record got wind of what we were up to, and they wrote this article, cover of Engineering News Record magazine, Calculated Risks. And the article was almost a dare. It was almost like, you think you're going to do something nobody's ever done before and you're going to do it at this scale? Are you crazy? That was the gist of the article. But we were undaunted and we thought, yep, we're going to do it. We have a proven team. We have confidence. And what they didn't know is we had about 10 years of research already in our pocket. We'd been working with the Charles Pankow Foundation. We've been working with Purdue on a series of research projects leading up to that moment, initially starting with Professors Bowman and Krager at the Bowen Lab at Purdue. In the early mid-2000s, 2005, 2006, we started some testing of the parts and the pieces, and here you see a 5-story tall T-shaped wall that we tested under seismic loading. And then more recently, testing a variety of loading conditions on these panels to the extent that, I ran out of slides. Sorry, I hit one too many buttons. Brandon, if you could back it up to the very last slide. Where we have kind of come to today is with Dr. Varma and his team. And starting at about 7 or 8 years ago, we connected with Dr. Varma, who was also doing research in this particular area of composite construction. Here he is with his team, and launched a whole nother series of research projects seeking to better understand and better perfect the ideas of this system. So what it is this 58-story building. Why we did it is to go faster, to squeeze that lag out of the construction sequence with the leading core and the steel behind. And now we're going to tell you how we did it. And how we did it was really founded in research that we did collaboratively with Purdue University, in particular with Dr. Varma and his team. So Dr. Varma, I'll let you take it from here.
Thank you, Ron. Thank you so much, Ron. It's a really tough act to follow. I guess I'm going to take your cue and I'm going to stand here and do the presentation. Thank you so much for the invitation. It's a real pleasure for both myself and Ron to be here and provide this distinguished Paul Zia lecture. We are inspired by Dr. Zia and all the research that he has done over the years. And in many ways, this research that I'm going to talk about is an example of the kind of work that Dr. Zia has done throughout his career, which is an interaction, a collaboration between industry and academia. It allows for graduate students to work on real projects. It allows faculty like me to interact with engineers like Ron and understand what the real challenges and issues are. There we go. So as I was planning for this portion of the presentation, I talked to Ron about, we've worked on this topic for so many years. There is so much information that is out there. We decided that I was going to pick 9 topics and talk about them for 5 minutes each. It's a tall order, so every 5 minutes the topic is going to change. We're going to talk about some of the important topics that revealed themselves as we worked on this collaborative project for steel concrete composite construction as applied to high-rise construction. Some of the topics that I'm going to talk about are designed for construction loading. This is going to be an important topic we're going to see in just a moment. Designed for local buckling and axial compression. Recommendations for stiffness. Calculating the flexural strength and ductility. Calculating the in-plane shear strength, which is going to be a big topic. Detailing of the coupling beams, particularly for local buckling. A capacity design principle for the seismic design of the system. Connection performance and detailing, and finally ending with the fire resistance design of this system. So we kind of covered the waterfront on the various topics, and this is just a brief listing of some of the research topics that we had to address in order to move forward with the system and bring it into a reality. One of the important aspects of projects like this is that there is usually a peer review committee that is assembled in order to check what is being done, in order to provide review comments and so on. And usually the peer review committee is pretty daunting. And so was the case for the Rainier Square project as well. We had a very strong review team. And so all the research that we did and presented and all the information we presented was scrutinized and really needed in order to get the approvals and move forward. Just to summarize, these are the key components of the speed core walls. It's a pretty simple system. It consists of steel plates, tie bars, shear studs, and the concrete infill. These are the 4 essential components, out of which the shear studs are actually optional. You may have a design that doesn't have any shear studs, which is really the case for Rainier Square. We provided some requirements for the steel plates. Right now, the emerging codes from the 2022 version are going to tell you that you must have a minimum reinforcement ratio of about 1% for the steel plates, and about 10% is the maximum reinforcement ratio that is permitted. Both the steel plates have to be connected to each other using ties, and these ties can consist of bars or steel shapes or structural steel members for that matter. The steel plates must be anchored to the concrete infill using stud anchors or ties or a combination of both. That's a requirement of the system, and the steel yield strength can vary from about 50 to 65 KSI. Now, one of the key components of this system are the tie bars. There are hundreds of thousands of these tie bars, and they have to be connected to the steel plates. They serve multiple purposes. They provide stiffness and stability to the empty steel modules, which is an important criterion for them. They provide resistance to the hydrostatic pressure when you cast concrete. They serve as anchor points for the steel plates after the concrete hardens, and you have to look at local buckling considerations. They provide structural integrity to the overall system, and if needed, they can provide out-of-plane shear resistance as well. So the first topic that I want to talk about is the design of this system before concrete placement, the topics of erection stability, transportation, handling, and so on. So research focusing on the stiffness and the stability of empty modules was conducted as part of the first Charles Pankau Foundation project, which Ron presented, that was led by my colleagues, Professor Bowman and Kreger. We picked up the thread from them and started looking at what we could do in order to design these systems. So we looked at the stiffness of the empty modules during transportation and handling, and more importantly, the stability design of these empty steel modules for the construction loads. So a lot of this presentation, I'm going to talk about some of the research, but I'm going to talk about it very briefly. So I'm going to let you know the publication that has presented this research in excruciating detail. For example, this is the paper that talks about the steel modules and their behavior, stability, and design. What we found from our studies was that the empty steel module flexibility is governed by the effective shear stiffness, which is associated with Vierendeel truss or frame action associated with the tie bars. Looking at the experimental data and the numerical models, we were able to develop equations for calculating the stiffness of the empty steel module. And what we found was that its shear stiffness was the key. In fact, the shear stiffness was far more important than the flexural stiffness of that empty module. And then we started looking at the stability of this empty module for construction level loads, and we found something fascinating in that. We found that the stability of this empty module is also fully governed by that same effective shear stiffness. This stability was found to be governed by shear buckling, and P critical for these empty modules was equal to GA effective, irrespective of the length and the end conditions. I still remember when we came up with this finding, I couldn't believe it for a moment, and I had to go back to all the theory and discover what was going on. And then I called Ron and I said, Ron, I think there's something interesting going on with this system. And we were able to understand the stability of this empty module and how it was independent of length, independent of boundary conditions, and governed solely by the shear stiffness of an individual unit that was part of the system. So we were able to harness this understanding and develop equations for predicting the stability of this empty steel module. And research, for you just saw the testing that had been done by my colleagues earlier, that experimental data combined with numerical models, we were able to combine all this information in order to develop simple recommendations for the design of this system as an empty steel module in order to have adequate stiffness and strength during concrete placement. So this minimum GA effective is now part of the code recommendation. So when the AISC 360 specification 22 comes out, you will see that it provides a tie bar spacing divided by plate thickness limiting equation, which is based on the shear stiffness of the individual empty module, which is a function of the flexural stiffness of the plates divided by the flexural stiffness of the tie bars. It's pretty fascinating. But after the concrete hardens, the stability of the steel plates follows a slightly different behavior. And the stability of the steel plates, when it is subjected to compressive stress, is governed by the local buckling that occurs in between the ties or shear studs after the concrete has been hardened. So the local buckling of the steel plates should not occur before yielding occurs in compression. So we decided that from a design perspective, we're going to make sure that these steel plates are compact or non-slender, which means that they will yield first and then local buckling will occur in compression. This research also led to the equations for calculating the axial compressive strength of the composite walls. So this is the second topic that I'm talking about, where we're looking at the same system, but now the concrete has been cast and it has hardened, and we're looking at the local buckling of the steel plates in between the tie bars. This work is summarized in another publication that I've highlighted here from the Journal of Structural Engineering that presents it in excruciating detail. What this research shows, and this is a compilation of all the experimental data from Japan, from Korea, from China, and from the United States. We took all this experimental data and combined it with our own numerical finite element analysis and test data in order to look at what was causing the local buckling of the steel plates and what would it take to modify the slenderness of the steel plates so that it would yield first and then undergo local buckling and compression. We were able to compile all of this experimental and numerical data and develop a simple recommendation for the slenderness requirement for the steel plates in the post-concrete cast and hardening phase. These requirements, if met, will give you a steel plate that is going to be non-slender, which means that it will undergo yielding before it undergoes local buckling. At the same time, we also did provide an equation for estimating the F critical or the local buckling stress associated for the steel plates, and we provided equations for estimating the axial compressive strength of the steel plate. after the concrete has been cast. So we started off by looking at the detailing of the tie bars before the concrete has been cast, and then we ended up looking at the slenderness of the steel plates after the concrete has been cast. And together, these two pieces of information provide us with pretty much all the information we need in order to detail the system. What should be the diameter of the tie bars? What should be their spacing? If shear studs are used, they're only going to work after the concrete hardens. The shear studs cannot help you while there is no concrete in the system. So you can add shear studs, but they'll only help you after the concrete has hardened. Tie bars will provide support both before the concrete hardens and after it as well. So taking all of this information, I'm showing you here an example calculation for a 24-inch thick wall with about a half-inch thick steel plate and with diameters of the tie bars being about 1 inch. You go through the calculations, and what you find is that there are two design options that are possible. One is with 1-inch tie bars that are at a spacing of 14 inches. If you did that design, it would meet the requirements of the empty steel module before concrete casting. It would meet the requirements of local buckling and axial compression after the concrete has hardened as well. And at the same time, you would meet all the minimum requirements for the steel and the concrete. On the other hand, you could go with a design that increases the tie spacing to about 24 inches. That would reduce the number of tie bars by a lot, but you would have to provide shear studs in between the tie bars at a spacing of 12 inches. So this gives the engineer multiple options to consider while detailing this system. So we talked about the requirements for the steel plate, the minimum reinforcement ratio, the maximum reinforcement ratio. We looked at the requirements for the tie bars and also for the shear studs that are applicable before concrete casting and after concrete has been cast. Finally, looking at some of the requirements for the concrete, we usually, in the design of this kind of a speed core system, use self-consolidating concrete with compressive strengths of about 10 KSI. This is commonly being used for most of the applications. There are no additional requirements for the concrete, and the concrete hydrostatic pressure when the concrete is cast is resisted by the steel plates and the tie bars. So this puts together all the detailing requirements for the system that consists of only 4 simple elements: the steel plates, the tie bars, the shear studs, which are optional, and the concrete infill. Once the engineer has come up with the design for the system, the next topic that they need to address is analysis and design. So we're going to take a look at some of the recommendations for how to go about modeling the system and analyzing it for the calculation of design demands. So we need recommendations for the stiffness of this composite system, because we want to conduct analysis in particular to calculate the design demands, which means that we need recommendations for calculating the stiffness of that elastic model. And we also need recommendations for estimating the in-plane flexural strength and the in-plane shear strength of the system after the demands have been calculated. So over the next few minutes, I'm going to talk to you about the recommendations for stiffness, how to calculate the in-plane flexural strength, how to calculate the in-plane shear strength, and also what will be the ductility of the system. All of this information is again summarized in a publication that you can download and look at from the ASCE Journal of Structural Engineering. I can provide a compilation of all the 9 papers that I'm going to talk about to the committee so that you can get access to them if you wish. So looking at the recommendations for stiffness, the stiffness recommendations should account for concrete cracking corresponding to the required strength level. We looked at the behavior of the system and we analyzed it for multiple loading conditions. And at the end of it, we looked at the section moment curvature response, particularly the secant stiffness corresponding to about 60% of the moment capacity of the cross section. And based on that, we provided some simple recommendations for modeling the system while conducting analysis to calculate the design demands. This includes the in-plane flexural recommendation, EI effective. What you'll notice is that the concrete has a contribution of only 35%, acknowledging the fact that it's cracked concrete. We're providing a recommendation for the axial stiffness, which again is 0.45. These two numbers actually correlate very well with each other. They're based on the same amount of concrete cracking. And for the in-plane shear stiffness, we recommended just using the full uncracked composite stiffness of the section, because it doesn't really matter for the applications that we are looking at. For high-rise building applications, the system is going to be flexure critical. So these are the recommendations for stiffness that we developed based on the research. And I'll show you some of the test data that validates these recommendations as well. Now, of course, you can have a design where the extent of concrete cracking may not be as much as represented by these equations, in which case the code and the commentary both tell you that if drift governs or if the walls are significantly over-designed, you always have the option of doing an analysis to estimate the amount of cracking and then use an appropriate stiffness value for the composite system. But in the absence of better information, you can use these recommendations for the stiffness. In terms of calculating the in-plane flexural strength, we recommend the plastic stress distribution method over the composite cross-section. You're looking at it here. The steel in compression and in tension is assumed to develop Fy. This is only possible because in compression, we made the steel plates compact or non-slender by meeting the requirements that I talked about earlier. That's why it can form Fy in compression as well. The concrete in compression reaches about 0.85 F prime C. You use equilibrium to calculate the plastic neutral axis and then the plastic moment capacity. Equations such as this are given for multiple different composite sections in the upcoming design guide. When you combine this with axial compression, the in-plane flexural strength is calculated using the recommendations that are typically used for composite columns or composite beam columns, which corresponds to the axial compression point A, the flexural capacity point B, the balance point D, and of course point C, which has the same moment capacity as point B. You can develop the PM interaction for this composite section, kind of similar to the way you do it for reinforced concrete, but using composite section principles, and those have been identified here. So depending upon if you have an axial load in compression of about 10%, 20%, or 30%, you can have different in-plane flexural capacities, which we'll talk about in just a moment. So having looked at these recommendations for stiffness and strength, we all want to know whether this is really based on test data and validation or not. The experimental data plays an important role, of course, in all of this research. So we developed some specimens that were about 1/3 scale representations of the full-scale steel plate composite walls, and we tested them in our laboratory under axial compression and cyclic lateral loading using actuators. You're also noticing the fixed condition at the base of the wall, and this is the location where plastic hinging will form. In summary, this is the lateral load versus displacement response of the specimen that I just showed you. And what I've done is gone ahead and identified the occurrence of various events along this load displacement response, the yielding of the flanges, local buckling of the flanges, local buckling of the webs, fracture initiation in the flanges, and then finally, total fracture of the flanges. So this gives us a good sense of what the lateral load versus displacement response of this system is going to be, experimental data that you need to show in order to validate the behavior of the system. I also have some photographs. For example, these are behavior during the 2 delta Y cycles, and you can see the initiation of compression flange local buckling, which corresponds to point B. You can also see initiation of local buckling in the webs, which corresponds to the 3 delta Y cycles and point C. You can also see the occurrence of fracture, which is point D, right through the flanges right here. And then finally, you get total fracture through the flanges, and you start getting the concrete to ooze out. So the experimental behavior of this system is very important to understand as well. And the experimental data does provide that information to us. Taking this experimental data, we were able to develop the plastic hinge versus rotation response. This is the moment versus base rotation, or the plastic hinge rotation response. And the backbone of that is shown right here, along with the occurrence of various events which tell us more about the behavior of this specimen, and in particularly how the ultimate capacity is being reached. And what we found was that the recommendations for stiffness and strength compared very well with the experimental data. For example, I'm showing you here the experimentally measured moment curvature response, which is shown with these dotted lines, and the solid black line is a simple fiber analysis of the cross-section, which compares very well with the experimental data. In fact, we could take that section fiber analysis and identify the occurrence of various limit states. For example, when does the steel reach a value of strain equal to 0.003? When does the steel reach a value of strain in compression equal to 2 epsilon y? We were able to identify the occurrence of various events. And what we found was that the peak strength was reached when the steel in compression reached a strain of about 2 times the yield strain. We were able to learn this from the experimental data. Similarly, we compared the stiffnesses that we got from the experiments with the recommendations that we had provided in AISC and also the EI effective equations that you saw earlier. And we were able to verify that those recommendations for the stiffness, the equations that you saw earlier, were indeed based on experimental data. From all of this experimental research, we were also able to look at the rotation capacity or the ductility of this wall at the base plastic hinge. I'm showing you here results from about 5 different tests that are showing the ratio of the moment with respect to the plastic rotation capacity of the hinge at the base, showing rotation capacities that were in the neighborhood of about 0.015 or about 0.02. And as the axial load increases, the rotation capacity decreases ever so slightly. So we were able to use all this information from the research in order to verify the equations for stiffness and the equations for strength. So AISC now recommends the plastic stress distribution and also permits the use of fiber analysis to estimate the in-plane flexural strength of the wall specimens. It tells you that if you have axial load, you need to account for that, and it gives you equations for estimating the flexural stiffness of the wall specimens that is based on this research as well. In the commentary, it points out that the plastic rotation capacity of the planar wall specimens was in the range of about 1.5 to 2% in radians, and the moment curvature responses compare very well with the fiber-based models, and tells you some more recommendations on how to calculate the in-plane flexural strength. So this is really good. We talked about how to detail the cross-section, we talked about how to estimate the stiffness, and then, of course, the estimation of the in-plane flexural strength. But then, of course, there's the big question of what is the in-plane shear strength of this composite wall system. Now, this was a major topic for squat shear walls, which are typically used in nuclear construction. I'm not going to talk about that here today, but there was extensive research done in Japan, South Korea, China, and even in the United States, looking at the in-plane shear strength of this system. As part of this research, we developed numerical models, mechanics-based models, and then, of course, experimental results, which led to comprehensive design provisions. So I'm going to touch upon that. Just briefly, there's a publication that talks about this in detail, the in-plane shear strength of this particular system. And what it comes down to is that the behavior is governed by mechanics, the orthotropic composite mechanics of this system. When you have this system subjected to pure in-plane shear, the tension component of that in-plane shear causes cracking in the concrete, and the compression is resisted by that cracked concrete. Together, you get an orthotropic system with zero stiffness contribution from the concrete in the tension crack direction and with almost complete stiffness in the compression axis. We were able to put all of this together into a simple mechanics-based model that resulted in an in-plane shear trilinear curve that explains the in-plane shear behavior of this system, which provided equations for that stiffness for the composite section before cracking, stiffness after cracking, and the in-plane shear strength, which corresponds to the limit state of von Mises yielding in the steel plates, resulted in this equation for calculating the in-plane shear strength. This equation was verified through large-scale testing that was done in our laboratory. Here I'm showing you a comparison of the trilinear curve with the backbone of the experimental data that we obtained from the in-plane shear behavior of this stocky or short squat shear wall. Besides that, after the testing had been completed, we removed the steel plates in order to examine that those 45-degree cracks were indeed forming, and we also identified the principal strains that we were measuring on the steel plates to be anchored right around that 45-degree point in both directions. Using this equation for the in-plane shear strength, we were able to collect all the experimental data from Japan, China, South Korea, and of course the United States. And we were able to develop a simple equation for conservatively estimating the in-plane shear strength of these walls. And these equations are now included in the AISC specification. And this is showing you the comparison of the experimental database with that. All right, so we covered quite a bit of material. We got a chance to look at how to detail this section. We got a chance to see how to model its stiffness, how to calculate its in-plane flexural strength, and also its in-plane shear strength. But really, we're talking about a system. And in this case, what what this slide is summarizing is that this system can be coupled or uncoupled, and the same system can be coupled in one direction and uncoupled in the other direction, particularly when you're looking at for high-rise applications. So I'm going to talk a little bit about the coupled system now and the coupling beams, which are also composite concrete-filled steel tubes. So you're getting a chance to see here the composite wall and the coupling beams, which are also concrete-filled steel sections. The coupling beams are identified here as rectangular box sections, and a picture of the walls is shown here. This is a segment or a portion of the coupled wall system, which is quite representative of the modules that will be built and shipped to the site for assembly, stacked on top of each other in order to make the system, which Ron is going to show in just a few minutes here. Besides that, those composite coupling beams have to meet certain compactness requirements, particularly for the flanges and webs. They are required to be flexure critical. So this is a little different from the coupling beam requirements that are used for reinforced concrete system. We require these composite coupling beams to be flexure critical, not shear critical, which means that their shear strength has to be greater than their flexural strength multiplied by 2.4 divided by the length of the coupling beams. There are also compactness or requirements for the flanges of the coupling beams and for the webs of the coupling beams that take into account local buckling of the flange in compression and web shear buckling of the webs for these composite coupling beams. So all of these requirements are now included in the seismic provisions. Talking about the seismic provisions, most of you are familiar with the seismic design factors R, omega naught, and CD. R is a response modification factor which is used to reduce the seismic design forces to an elastic level to account for the inelastic behavior and ductility of the structure. Omega naught is the overstrength factor which is used to estimate the inherent overstrength in the system. And CD is the displacement amplification factor that is used to calculate the inelastic story drift from the calculated elastic story drifts. So these R, omega naught, and CD are going to play an important role moving forward in our discussion. ASCE 7 provides these seismic design factors for most steel, concrete, and composite systems. In fact, for the uncoupled system that is only with shear walls, no coupling beams, ASCE 7 includes values of R equal to 6.5, omega naught of 2.5, and CD of 5.5. On the other hand, for the coupled system, ASCE 7 did not include any values, which means that we had to develop the factors and provide the research backing in order to provide these R, omega naught, and CD factors for the coupled system. We found that in ASCE 7, the largest value of R for any system is 8. So this became the target for the coupled speed core system. We needed a comprehensive design method to maximize the system level ductility, which gave us an opportunity to develop a capacity design for the system. How often does that happen? We have summarized this capacity design principle for the coupled composite plate shear wall system in another publication in the Journal of Structural Engineering. We identified two sources of inelastic deformations. You can form flexural plastic hinges at the ends of coupling beams, and you can also form flexural yielding at the base of the walls. Our preferred mechanism, inelastic mechanism, was to form flexural plastic hinges at the ends of both coupling beams and at the base of the walls. But we decided to implement a strong wall, weak coupling beam design approach in order to size the composite members. What this means is that you develop extensive plastic hinging in most of the coupling beams along the height of the structure before you get significant yielding and fracture at the base for the walls. The coupling beams can even fracture while the walls continue to provide inelastic behavior. So what does this really look like? I'm showing you here the capacity design principle for this coupled speed core system. Point A corresponds to your ELF, your equivalent lateral force level. We're designing the coupling beams to reach the capacity at this point, but the walls are not designed for the forces corresponding to point A. Instead, the walls are designed for the capacity corresponding to point B, where we get plastification of all the coupling beams along the height of the structure. So the walls are designed to be stronger. They're designed to develop the plastic mechanism in the coupling beams. Eventually, if you keep pushing on the system, you reach point C, where you form plastic hinges at the base of the walls. And by the time you get to point D, you start getting fracture in the coupling beams and eventually fracture in the walls. So this was done to distribute the plasticity along the height of the structure. And we want to distribute the plasticity along the height of the structure because doing that gives me a more ductile system, which will allow me to reach an R factor of 8 rather than 6.5, which is being used for the uncoupled system. We implemented this capacity design principle in order to design several archetype structures. And I'm not going to talk about the details of all of those, but I'm showing you here the pushover behavior that I get from a 2D finite element analysis, nonlinear and elastic finite element analysis of this coupled core wall system. And again, point A corresponds to the ELF level load. Point B corresponds to the spread of plasticity along the height of the structure in the coupling beams. And point C corresponds to the formation of plastic hinges at the base of the walls. So we get that behavior that we had programmed into the system using the capacity design principle. But this is just static pushover behavior. So we really wanted to see the behavior of the system to dynamic earthquake loading. So we did a series of nonlinear time history analysis. I'm showing you here the response from one of those earthquakes that we were considering. It's the Superstition Hills earthquake, and you're looking at about an 8-story structure. We scaled the ground motion to be a design basis earthquake, and what we found was that all you were getting was some yielding in the coupling beams along the height and some yielding at the base of the walls, which is what you'd like to see for the design basis earthquake. When you make the earthquake larger, by changing it to the maximum considered earthquake, the response shows that you get more yielding of the coupling beams and it propagates along the height of the structure, which is what we want. The more you dissipate plasticity along the height of the structure, the better the earthquake behavior, the better the ductility, and the larger the R factor. So we were able to achieve that by spreading the plasticity along the height. You do still get some formation of plasticity at the base of the walls. But when you consider the failure level earthquake, all those events that we had identified occurred in the right sequence. You get yielding of the coupling beams, followed by wall yielding, propagation of yielding along the height of the structure, initiation of fracture in the coupling beams, and then finally total fracture of the coupling beams along the height of the structure. So that was the seismic response that was programmed into the system by the capacity design principle, and it gives us exactly that. This is a video that actually shows the seismic response of a 12-story structure where you can see the ground motion as it's tracking through, and you're seeing the response of the system. And all of these red spots are the occurrence of yielding along the height of the structure. There's the big pulse that causes all kinds of yielding along the height of the structure. And when the shading turns black, that's when you're getting close to fracture in the coupling beams, which is occurred for some of these coupling beams along the height. Remember, this is the failure level earthquake, but the system remains stable and survives the entire failure level earthquake with some occurrence of fracture initiation at the base of the walls at the end. So we conducted FEMA P695 studies, which is the methodology to develop the R, omega naught, and CD factors for the system. Using the capacity design method, we developed archetype structures, 8, 12, 18, and 24-story. All of these archetype structures were reviewed by Ron and his team. They made sure that we had representative designs of what would be built in the real world. These were modeled using 3 different independent approaches by teams at Purdue University and at University at Buffalo. And we did hundreds of thousands of nonlinear time history analysis for 44 scale ground motions with increasing intensity. We conducted a statistical analysis of the results from the FEMA P695, and the results from all of that are summarized in this publication. And eventually, all of this research was presented to the ASCE 7 committee, to the Seismic Structures Committee, and also to the Provisions Update Committee, which was reviewed and provided comments and accepted into ASCE 7 with an R factor of 8. That's the victory. The CD factor of 5.5 and omega naught factor of 2.5 were given based on the studies that we had conducted. The seismic design and detailing requirements for this system are provided in AISC 341, that's upcoming publication, and the performance requirements for the coupling beam to wall connections made in the system level analysis were based on what we saw from the nonlinear time history. Eventually, the required coupling beam rotation capacity was 0.03 radians. This is the requirement for the connection between the coupling beam and the wall, which actually brings us to the topic of how do you connect these composite coupling beams to the wall connections. So we looked at several designs for the composite coupling beam to wall connections. We had them reviewed by practitioners, Ron's team, the fabricators. Everybody looked at them and told us which ones were good enough to be considered realistic representations of design. Typically, the coupling beam flange plates are penetrated into the walls, and I'll show you a picture of that in just a moment. But the performance requirement for this coupling beam connection is that it should have a rotation capacity of about 0.03 radians before the moment capacity drops below 80% of MP. So that's the performance requirement for this coupling beam to wall connection. We looked at many different connection types. I'm showing you only two here on this picture. In both cases, the coupling beam flanges are going into the walls and they're CJP welded to the plates of the composite wall. There are two different options for the coupling beam webs. Here, the coupling beam web is continuous. It's actually the same plate as the web for the composite wall. And in this one, the coupling beam webs are lapped from the outside and fillet welded to the plates of the wall. So two different connection types that we are looking at here. Of course, we looked at many more than 6 different connection types, which I'll summarize in the end. Here, we conducted experimental investigations to make sure that these connections, when designed, would have the rotation capacity of at least 0.03 radians. I'm showing you here the test setup, which includes the actuators, the coupling beam segment, the wall, and then, of course, the connection between the coupling beam and the wall right here. Summary of the lateral load displacement response from these coupling beam to wall connections. Once again, very similar, lateral force versus beam end displacement. And the occurrence of various events along the lateral force are identified here, including yielding of the flanges, initiation of fracture, local buckling of the flange and the web, and then total fracture of the flanges. We took this force displacement and converted it into a normalized moment versus chord rotation response. And there's the line corresponding to 0.03 radians, which was the performance requirement for this connection. So we took these experimental results, and I'm showing you here a couple of photographs. You can see the formation of local buckling in the flanges of the coupling beams. You can also see the occurrence of fracture right there in the flanges and portions of the web as well. This occurs at a chord rotation of 0.035 radians. We took the envelopes of the moment rotation responses and we plotted them so that we could look at what was the rotation capacity of the connection. For example, this connection had a rotation capacity of 0.037 radians, which corresponds to the reduction in the moment capacity of about 80% of MP. So we were able to identify the performance of these connections. As I told you, there were 6 different connections that we've tested, and all of these have passed the requirements that we've placed on them, which is a rotation capacity of 0.03 radians. You can look at the details of these connections in some of the publications. And we come to the last and perhaps the most important topic for this composite speed core system, which is what is the fire resistance? Because the steel plates are located on the outside, there are questions about what will be the fire performance of this system. So we focused on unprotected composite walls. Between our discussions with Ron and his team, we identified that what was really going to make this system efficient was if it could be used without any additional fire protection. So that's where we focused on. We conducted experimental tests, which included looking at the thermal behavior and the structural behavior to both uniform and non-uniform heating. And we developed numerical models that were benchmarked to the experimental data and then used to conduct parametric studies. At the end, we were able to develop wall axial strength equations as a function of temperature and fire resistance rating in hours for the system, and also provide recommendations for steam vent holes for the system. All of this research is summarized in a Charles Pankow Foundation report that you can download. It's available free on the web, talks about all the experimental results and numerical results. And I'll summarize them rather quickly. This is showing you a structural test setup for the wall. It is being subjected to axial compression using the self-reacting test setup. And then it is covered by what are ceramic fiber radiant heaters, which I can control the temperature versus time response of on the surface of the steel, that are completely covering up the wall and subjecting it to different time temperature curves depending upon whether it is uniform heating or non-uniform heating. A photograph of this test setup in the laboratory is shown here. You're seeing the heaters that are completely enveloping, so you can't really see the wall. It's behind the heaters. And this is a photograph of the experiment in operation. You can see the red hot portions that are subjecting the heaters are heating up the wall specimens. It's almost red hot behind the heaters. You're also seeing some moisture coming out from the concrete as well. The typical experimental results, I'm showing you some of the thermal results. The surface temperature of the steel reaches about 1000 degrees centigrade, which is what you'd want to see in a fire test. But the thermal gradient through that composite section is shown here, while the steel surface temperatures are about 1000, towards the center of the wall, the temperatures are much lower. And this was only a 9-inch thick wall. That's not very thick. It's actually a 1/3 scale model representation of the wall. So we found that that concrete provides a very strong heat sink for the system, to the point where, in spite of all the load that had been applied to it, the specimens never failed and had fire ratings in excess of 2 hours for the 1/3 scale 9-inch thick specimens. Here are some photographs of the specimens. You can see the local buckling that has occurred in between the tie bars in the steel plates. That's a close-up of that, locations of shear studs and tie bars and the local buckling in between. And using these experimental results, we were able to develop 3D finite element models that were benchmarked to the experimental data. And these benchmark models were used to conduct parametric studies for a wide range of data, for a wide range of parameters, including geometric parameters, material parameters, and so on, and boundary conditions as well. The results from these numerical parametric studies are summarized in a publication that has just become available. This came out, 2 days ago? But you can download it to look at it. I can make the slide move forward. There we go. The results from the parametric studies were as follows. We found that the wall slenderness ratio, the wall thickness, the load ratio, and the type of boundary conditions significantly affect the failure times. Walls with slenderness ratios higher than 10, which means that the story height divided by wall thickness ratio greater than 10 fail due to global buckling. The middle region of the concrete infill takes much longer to heat up in thicker walls, resulting in very high fire resistance, and limiting the steel plate slenderness ratio can marginally improve the fire resistance of the walls. Next slide, please. We also conducted studies on non-uniform or one-sided heating, which we found results in thermal bowing, some second-order moments in the walls, and some eccentric moments as well. Walls with height to thickness ratios greater than 20, what I mean is story height divided by wall thickness ratios greater than 20, and subjected to one-sided heating, need fire protection on the exposed surfaces. But this never happens because of the thicknesses that are generally used in construction. Typical wall story height to thickness ratios are within 5 to 10. So this is just providing a theoretical limit on how far you can go. And what we concluded was that the typical speed core wall designs do not need any fire protection. They can be designed unprotected. This information is, you'll have to press a few times. Thank you. Please go ahead and press one more time, and one more time. Thank you. We also developed a computer program for estimating the fire design of these composite plate shear walls. One more time, please. This computer program can be downloaded from the link that is given at the bottom of the page. Can you press it one more time? There we go. This program is available for download from the Purdue University Research Repository. You can download the program and you can run various simulations for the fire resistance of your wall and check its design. And we used all of these results in order to develop the fire design equations. For example, we developed equations for calculating the compression strength as a function of temperature. PNOT is the compressive strength of the cross section. PET is the buckling strength of the wall. And together it gives me the axial capacity of the wall as a function of temperature. I can calculate the temperature from the fire and I can estimate the axial load capacity. So there are equations that are based on test data and numerical models that can be used to calculate the strength of the wall. Or if you are just looking for the fire resistance rating equation, we've developed that as well as a function of the applied loading, the H/TW, which is an important parameter, and the thickness of the wall. Together, including all of these parameters, you can calculate the fire resistance rating for the system, which is generally in excess of 3 to 4 hours. So that's the summary of all the research that we did. Well, it's not summary of all the research, but it summarizes some of the topics that we addressed as we were providing or generating this knowledge base for the system to be reviewed, including design for construction loading, design for local buckling and compression that results in the section detailing, recommendations for stiffness, for calculating the in-plane flexural strength and ductility, calculating the in-plane shear strength, detailing of the coupling beam to prevent local buckling, the capacity design principle for the coupled core wall system, the coupling beam to wall connection performance and detailing, and finally the fire resistance and design of the walls. So those were some of the topics I wanted to summarize to you today. I wanted to check that I'm over or under my time limit. So, Santiago. Thank you.
Thank you so much. We're going to take a very short stretch break here, 4 or 5 minutes, and then we'll come back. Ron's going to join us again on stage and talk about how this is applied for the construction of the Rainier Square Tower. So feel free to step out if you need to, but we'll start back in just a couple minutes. Thank you. Afternoon, everybody. Welcome back. Again, thank you all for being here. At this time, we're going to present our Paul Zia scholarships. So I'd like to welcome Dr. Mervyn Kowalski and Dr. Jason Patrick up, and they're going to introduce the scholarship recipients. And then we'll hear from Ron. Thank you.
Okay, thanks, Greg. As Greg said, we're about to announce the recipients of this year's Zia Scholarship. Before we do that, I want to just say a few words about the award. The award was developed to honor Paul Zia and his commitment to graduate education and his commitment to graduate students. I remember very fondly Paul Zia, when I was an assistant professor, inviting all of his students and myself to his house with Dora, and a means of really fellowship. And he always would put his students first. And this is a recognition of his commitment to his graduate students. The recipients, this year we have two recipients, and they are selected based upon the nomination of the structural engineering and mechanics faculty, who then give that nomination to the director of graduate programs, who makes the final determination. And this year, the committee has asked the advisors for the first time to introduce our recipients, and that's why we're here. So it's really certainly my privilege to introduce Jessie Tangjatam, who Jessie will soon be completing her PhD. She's studying earthquake engineering and seismic design of high-strength reinforcing steel. Jessie's goal is to be a faculty member, a professor of structural engineering. She's, as part of her work, she conducts large-scale tests and does computational modeling. And her work will ultimately end up in terms of providing recommendations to the California Department of Transportation. So just to give you a little idea of what Jessie's been up to in the last few years, she has mentored undergraduate students, taught reinforced concrete to a group of over 70 people, served as president of the Earthquake Engineering Research Institute student chapter for over 3 years, designed, constructed, tested, analyzed, and modeled over 12 large-scale test columns. She's received the ACI Fellowship. She's received the NSF Preemptive Fellowship to study earthquake engineering in New Zealand. She serves on the Earthquake Engineering Research Institute Student Leadership Council for several years. And most importantly, and maybe the most significant honor she's received, just about a month ago, we learned that Jessie received the Earthquake Engineering Research Institute, Federal Emergency Management Agency, and NEHRP Graduate Fellowship. And I cannot stress enough how significant this particular honor is. It is the highest honor that a graduate student studying earthquake engineering can receive anywhere in the world. There have been 20 such recipients over the last 20 years. And if you look at this list, it's an impressive list of people who have gone on to have really distinguished careers in earthquake engineering. Jessie is an inspiring member of our research group, all of whom are here to see her and support her in receiving this award. An amazing student, a wonderful person, and I'm honored to be your advisor. One last thing, Jessie is very humble, doesn't like a lot of attention. Probably not happy with me right now because I'm bragging so much. So I'm going to stop at that point. So please join me in congratulating Jessie.
Thank you, everyone. It's a real honor to announce this next award, to whom will actually be my first PhD graduate, Urmi Devi. Urmi left the position as a university instructor in the home country of Bangladesh to pursue doctoral studies here at NC State because of the renowned reputation of this institution and department, thanks in part to Dr. Paul Zia. Urmi's graduate research is in the domain of structural engineering, however, not on the size scale of structures we've seen today, but nearly 1/1,000,000th smaller in the micrometer range. Urmi has been able to merge the concept of biological microvasculature with fiber-reinforced composites to create dynamic metamaterials that exhibit multifunctional properties such as thermal regulation and electromagnetic modulation. Such structural materials are finding applications outside of this world, literally, on space probes and telescopes. Urmi's engineering curiosity and relentless perseverance has even led to a recent research article being featured on the cover of a prominent materials journal. Beyond scholarly research and a perfect grade point average, Urmi is a valuable group member, one who is collaborative and supportive to others and always willing to take time to help. Urmi played active roles in the Civil Engineering Graduate and Bangladesh Student Associations during her tenure here. I'm thankful to have Urmi as a member of my team and confident that she continue to make lasting contributions in industry, and happy to share that she's been recently offered a position at Intel Corporation to continue working at the micro level. So while her structural implements may not be physically large, her impact is certainly going to be immense as she embodies the next generation of Wolfpack engineers inspired by the contributions of Dr. Paul Zia and others. Congratulations, Urmi, on a well-deserved award today.
Thank you all so much. At this time, I'd like to welcome back to the stage Mr. Ron Klemenchik.
Hi, everybody. I'm back. Couple of things I wanted to summarize for you. What you just were witness to from Dr. Varma was 15 years of work that he presented to you in 45 minutes. And it's an amazing body of work. And I think he did an amazing job of condensing it down to 45 minutes. Secondly, engineering works. It really does. And when we started this whole process, none of this was in the building code. The system didn't have a name. It didn't exist. We made it all up. But we made it up based on science and physics and math and lots of hard work. And here we have this thing today we call SpeedCore, and it in fact is in the code. But it was a 15-year journey throughout all of that. So the point to all of that, though, is that engineering really does work. And you can use first principles, the things you learned in your undergraduate statics class, to think about and imagine new ways to build, and then apply that knowledge in a really meaningful way to make something new in the world. So that's kind of what we did. 3 is really important, and it hasn't been said yet. I don't think I'm going to say it, though, because I think it's really important. All of this stuff we're talking about today is public domain. None of this stuff is patented. None of it is proprietary. None of it is mine, and I own it, and you can't have it. From the beginning, we set out on this journey to make sure that everything we did, we shared with the entire engineering community in hopes that others would see value in it and, in fact, make it even better somehow. So all of these papers that Dr. Varma shared, all the research results, all of this stuff is available for free online. You don't have to subscribe. You don't have to have a Hulu membership or anything. You can just go there and get it. And, you know, somewhere in all of this deck probably is my personal email. You can send me an email and I'll answer your question. That was really important to us, that this is something that is to be shared with all to make it better. So I'm going to move on now and talk a bit about taking all of the science that Dr. Varma shared with us and applying it now to this real building and how we're really going to build something. Because even if I had the contractor sit through a 45-minute lecture from Professor Varma, I don't think he would have made it through the first half. Because all they want to do is, how big is it, where do I put it, and what kind of concrete do you want? So we're going to talk about that. All right, well, let's go back here for a second. So when we design buildings, calculating how strong it needs to be is about the easiest thing we do. The next more difficult thing that we do is to calculate how it might move. Move in earthquakes, move in the wind, move from thermal variations, move in different ways, move under its own load during construction. And then the third thing that's almost the most difficult in many cases, in particular the buildings we design, is how do you actually make the thing? Because it's one thing to like run a computer model and, oh, look, my computer says it works. Well, yeah, but how the heck do I build it? And so many things that we see today in modern architecture in particular is very, very difficult to actually build, to actually make it. And so how can we thoughtfully, pragmatically, and with efficiency and speed make things? So we set out on this project to solve those problems. How do we make this fast, efficient, effective, and something the contractors at the end of the day would report back to us and say, can we have another, please? So sitting with the contractors, and in particular in this case, the steel erector, we explained to him our idea of having these modularized panels that we were going to prefabricate, ship them to the site, and stack them up like Lego blocks. And they were going to be 14 feet tall and 30 feet long, and they were going to come together at the corners, and that's where he said, stop. I can't build that. Okay, what do you mean by that? So, well, something that large, 14 feet tall, 30 feet long, I can handle, but if I have to connect it at 90 degrees to another one of those, I can't physically do that in the field. I'm not able to make it plumb and true and be in the right spot. So instead, here's my suggestion. Let's fabricate 2-story tall columns at each one of the panel intersections, box columns, something that's smaller in size, easier to handle, something that I know how to erect, and I can put it there and I can make it plumb and true and in the right location. And then I'll use those 8, in this case, 8 box columns as a guide to allow me to fly the panels in, and then the panels, I don't even have to think about where to put them because I already have kind of the picture frame, if you will, set that I was able to control in the field with all of my surveying and field layout. So that's how we went about our business. Here you see 2-story tall box columns with single-story wall panels, and this was the strategy going in. Not something informed by the engineer, something really demanded by the erector, because he thought this was going to be the best strategy to make the building go. Engineering-wise, in this particular building, we had to size things. Well, how big are they? This particular building, given its location in Seattle, given its unique shape, given its slenderness, oddly, it was controlled by wind and not earthquakes. Even though we're very close to the Juan de Fuca Fault, even though earthquakes are prevalent in Seattle, this particular building was controlled by wind design, and by that, the stiffness of the building was imperative. That's what set the thickness of the walls. Not the strength of the building, the stiffness of the building. So the walls here varied from 45 inches thick at the base, very thick, to 21 inches at the top, and you can see we had 1-inch diameter rods at 12 inches on spacing, 12-inch spacing throughout everywhere. That was the cross-tie rods. When we started the design of this project, we were about a half, maybe not even a half, maybe a third of the way through the research program with Dr. Varma. We had results from Krager and Bowman. We had some initial results from Dr. Varma, but we were early days. We had enough confidence to proceed with the system, but there were still years of research yet to come to improve upon the system and understand it better. So during the design process, we had to make choices armed with engineering basics, our basic calculation, our intuition, and then conservative decision-making. And in this case, 1-inch diameter rods at 12 inches on center was a conservative choice. We felt in time research would prove we could use a wider spacing or smaller tie rod, but we didn't have the evidence at that time. And there were a number of decision points in the design of this project that at the time we designed it, this was about 2015 when we designed it, we didn't have all the research yet complete, but we still need to make the design decision. So that's why in this building, there's 1-inch diameter rods at 12 inches on center. There's 240,000 rods. Each of those rods connected to a plate on each side. You do the math, 240 times 2, 480, I can do the math. 480,000 connections. How we go about making those is really, really important. If we save 1 minute per connection times 480,000, it's a lot. So we sent out on this path with the erectors and the fabricators to kind of think about how that was all done. In addition, since no one had ever done anything like this before, we thought we need to practice. We need to go out in a yard somewhere, and we need to build a full-scale mock-up. In fact, not just one, but two. This first mock-up that you see here that we built was a section of the core, full-scale. It was made with wooden formwork. And the purpose of this mock-up was we need to understand the concrete we intend to put inside of it. How are we going to place it? How is it going to be consolidated? How is it going to flow? What are we going to end up with when we try and concrete this section at this scale? So here you see the crew out there trying to pump concrete from above. We mocked up the cross-tie rods with PVC pipes. The purpose of all of this was so that when we were done with this mock-up, we could take it apart and look at it. That's why this formwork was wooden. That's why the tubes were plastic instead of steel. And ultimately, that's what we did. We cast the concrete, and then we took everything away to prove to ourselves that the mix design that we had collaborated with the ready mix producer on, that it was placeable, flowable, that it would consolidate, that the idea of placing the concrete from above and letting it free fall 14 feet was going to be such that we didn't have any segregation problems, that in fact the concreting operation would be a success. The good news for us here it was a huge success. Everything looked perfect when we got done peeling the wall away. We learned many, many, many things. One thing that we didn't really think about, but we learned as a product of this mock-up, was when we went into the field to make these for real, that we needed to make sure all the construction workers anywhere close to this wore gloves and stayed away from it because of the heat of hydration. The concrete got to about 160 degrees in the heat of hydration, which transmitted through the steel plate. So if you touched the steel plate after we cast the concrete, you'd burn your hand, just like you touched the top of a stove. It all makes sense in the aftermath. They say, of course, Ron, why didn't you think of that? Well, you can't think of everything, right, until you go and do it. And so we learned many, many things, that just being one story, that we had to make sure the construction workers were going to be informed and safe during the construction process so they didn't all go home with second-degree burns. We also built a steel mock-up, a full-scale steel mock-up. So we prepared some drawings. Here we were going to build a corner of the core. We fabricated these steel sections in the real shop where the real fabrication was going to occur. In this case, it was in Portland, Oregon, so a couple of hours away from Seattle South. Here you see a couple of those columns, the corner columns being fabricated, the box sections. All of the circular holes that you see there, the Swiss cheese in the plate, are concrete flow holes. That's the inside corner of the box section. So as we place the concrete into the wall, that the concrete would actually flow horizontally through the columns and around the corner. And that's the purpose of all those holes there, is to allow that concrete to flow. We put all this stuff on a truck in Portland. Not a small task to think about interstate shipping with wide loads. These are 14 feet wide panels. The good news is both Oregon and Washington defined wide load versus extra wide load at 14 feet. We were wide, not extra wide. Why is that important? If you're extra wide, you need a police escort. At 14 feet, we were wide. We needed to have a lead car and a trail car behind the truck, but we didn't need to inform the state patrol. We could just roll it down the road. There's all sorts of lessons like that we learned or had to solve along the way, but they're all solvable. All right, so here's some more panels on the truck. And then we brought them to that same yard in Seattle and had the raising gang, the erectors who are actually going to build the building, come and practice. How do I tip this piece off the truck? Once I have it on the hook and swing it, how does it behave in the wind? How do I set it and plumb it and true it so that we can get it in the right place? You can see these panels are not small, right? These are full scale, 1 story tall with a splice there. And then we also experimented in the same mock-up with the splice itself. The details of the splice is probably a 2-hour seminar in and of itself. What we did here on this project is all of the field splices were welded. Again, a product of a conversation with the erector. We said, we can weld, we can bolt. Here's a picture, a couple pictures of a welded connection. Here's a couple pictures of a bolted connection. Which do you prefer? We can engineer either. Which of these do you prefer? In this case, the erector said, I much prefer to weld. And the reason he much preferred to weld, one is he had the crew to do it, and two is he felt that the field fit up and the ability to deal with small variations in the plate trueness would be much easier to handle with welding than with bolting. But he was much more worried about misalignment of bolt holes, and literally there would have been hundreds of thousands of bolts involved in splicing these sections together. So back reaming hundreds of thousands of holes versus taking up small variations in plate due to warpage with the welding was a far better proposition in his eyes. So we chose to weld. When we got in the field here, we asked the question, well, there's 32 miles of welding to do. Surely you don't want to do it with a guy and a stick. Surely you want to do it with some kind of semi-automated, mechanized, robotic something. Said, well, let's give it a try. So we did, and we experimented with it. And what we learned was that the robotic, semi-automatic welding apparatus work really well in shop conditions, where you're able to set plates or pieces on a flat table and get them all aligned perfectly and then do the weld. When you put this whole entire assembly into the field, where things aren't perfectly aligned and things are a little warped and a little bit out of plumb and true, the mechanized welding didn't do so good. So herein lies an opportunity for those of you who are into mechanized welding and robotics. Go figure out how to make a robot that can adapt in the field to misalignment of plate. I got 32 miles of it. Huge opportunity. Guess what? They welded it all by hand. 32 miles of it. And they did that because they felt that was their best opportunity for success. We got it built, we did these things. There were some conservative design assumptions or design decisions made. There were some conservative construction decisions made because we kind of weighed the risk and the reward. And in this case on the welding, the risks of trying to do something robotically in the field where we knew based on our mock-up that it didn't really work really well was something they didn't want to experiment with, so they hand welded the whole project. Next, we went into a shop drawing phase, just like any other project, so lots of detailed shop drawings were made. A typical panel you see here, 14 feet tall, 30 feet long with all the cross ties. Maybe more interestingly here were these H panels. When you look at this closely, you see a couple of other things. You see shear tabs that are welded in place to the panel to accept the incoming floor framing. You see the deck ledger angle already installed on the side of the panel to accept the incoming metal deck. So everything that would normally be put in the field on a reinforced concrete wall with embed plates and field welding and field attachment, all that was done in the shop. So everything to receive all the incoming parts and pieces was all shop fabricated and then trucked to the site, including mechanical penetrations for ductwork and piping. All of this was coordinated on paper, in the CAD, in the Revit model ahead of time, so that all the penetrations could be prefabricated into the panels in their right location, in the right size, and all that work done in the shop. So ultimately, all these panels started showing up on site. I had the unique, kind of crazy coincidental vantage point. That picture's from my office window. The project was literally right outside of my office. I could look outside my window every day throughout the construction of this project and see it from the very beginning to the very end, about 60 feet away from me. So the trucks rolled up and we started hoisting the panels into the foundation. And then the first thing we had to do was connect it to the base. In the case of Seattle, we're blessed with very good geotechnical conditions in the downtown area. We have very, very highly over-consolidated glacial till, has very, very high capacity. Back in the Ice Age, right, the glaciers were in Seattle and consolidated all this soil. So it has huge, huge bearing capacity, which allows us to found most of the buildings in downtown on a shallow mat foundation. So that's what this is. It's a mat foundation. It's 12 feet thick. So me on top of me, thick, that's how thick the mat is. That's what this core was anchored into. And so how we chose to go about anchoring it was a series of what we called stanchions or columns. You see them like a picket fence here. And those were to allow kind of the beginnings of the wall to take its position. It was really important to get all of this aligned perfectly from the beginning, because if you can imagine, if we got this wrong, the layout wrong from the beginning, and then started to propagate that over the next 900 feet of height, that would be really bad. So we spent a lot of time in the layout and in this connection and how it was anchored into the mat foundation 12 feet thick. Once again, a picture from my office. The mat is now cast. The wall's all set to go and are ready to go vertical now. So from this day, the day I took this picture and the steel showed up, and I have a video I'm going to show you here in a bit, from this day, which is basement number 7, remember I said we had a very huge basement, 7 basements, from basement number 7 to the roof is level 59. 59 and 7, 66. We erected 66 floors from level 7 to the roof in 10 months. It was originally, with the original idea of the building with a reinforced concrete core and a steel floor framing, it was originally imagined to be 20 months. So we thought we're going to save 10 months from this moment going forward. So here we are, we started building the building and up it went. Oh, by the way, take a step back. Hello, take a step back. See the building on the right? That's a whole seminar waiting to happen by itself. That's my office in that building. It's a very famous building in Seattle. It's called Rainier Tower. It was designed by a very famous architect, Minoru Yamasaki, same architect that designed the World Trade Center in New York. It has this pedestal base, 12 stories tall, very, very famous building. If you come to Seattle, you must go stand on the corner and do what all the other tourists do. It's frightening, but we live there and we know it's safe, so it's fine. But I got to look out the window every day down. I live on the 32nd floor of that building, so our office there. So up we went with our 2-story tall columns there you see going up and the speed core panels going in. And more steel erection, more typical. Now, we talked earlier about the outrigger columns. Remember the ski pole analogy from before? So the forces on those columns were also very huge. So we had to think about, well, how to make the columns. And we elected in this case to make the columns out of the same speed core assembly. In this case, the columns are 5 feet square, 5 feet by 5 feet. But we made them out of the same idea, same concept of a steel plate. That steel plate interconnected with cross ties, in this case in the form of a closed box. So you see all of the little dots on the side, right? Those are all the cross ties that are protruding through. So this is a 5 foot thick, or a 5 foot square box of 1/2-inch thick steel plate, then filled with concrete, which provided the strength and the stiffness for the outrigger columns. So it's the same, essentially the same process, same technique. This picture gives you a few other hints. And if you look really closely, see if I can use which button is the pointer? The red one? There we go. If you look right there, or better yet, maybe down there, you see that dark circle? That's a placing port. What that is a circular hole in the side of the speed core panel where we put the concrete pump. And in each of the corner columns, in each of the 8 columns, there was a placing port. And we were able to put the concrete pump, the hose, into that hole and pour the concrete in through that hole downward into the core wall panel below. And we did that floor by floor by floor. So each casting of the wall was a single story high. But that's how that was done. Looking again down from my office, you see the core starting to take form and getting closer and closer to where I worked. And now one day, magically, the core was right there out my window. Again, if you look really closely at this image, you'll see there's a placing port and a placing port and a placing port. You see the 2-story tall columns going up. And this is kind of the basic assembly of how the construction went. What you don't see, as compared to that picture I showed you in the beginning, is the core is not 20 stories ahead of the steel erection. The core is right with the steel erection, and they're going hand in glove as we go up the building. And this was part of the speed. So we were achieving our goal. Kind of a closer up view of that same thing. Dr. Varma mentioned, I'll kind of go back a slide here for a second. Hello? Yeah, Dr. Varma mentioned one of the design considerations for us was the stability of these sections, these wall sections, in the unconcreted condition. This is actually a design parameter for the engineer to think about and the contractor potentially inform. On this project, in that discussion with the contractor, what we all targeted was the contractor wanted to be able to erect 8 floors of steel, not just the core, but the core, the floor beams, and all the metal deck. I want to erect 8 floors of it before I must concrete the wall. This was one of the controlling design variables for the size of the cross ties and their spacing, because it spoke to the temporary stability of the unconcreted section wall panel. That's something you can dial up and dial down. You can say, oh, I only need 4 floors, or I want 12 floors. How many floors of construction load do you want to support with the unconcreted section is a design variable that needs to be considered in the overall. So again, it's not just making it strong enough, it's figuring out how to actually make it. So I spent a lot of time talking to the contractor about that. One of the other things I mentioned earlier was about the outrigger trusses and the difficulty of connecting an outrigger steel truss to a reinforced concrete wall back to another outrigger truss. In this case, all those connections were shop fabricated. All the plate sections were done, all the gusset plates, this big node that you see here, all of that was shop fabricated, so when it came out to the site, it was all done. It didn't slow the construction that would otherwise have been painstakingly slow if we were trying to embed all of that in a reinforced concrete wall. Whoops, sorry. Similarly, at the outrigger columns, the gusset plates, the incoming connections for the outrigger trusses themselves, all shop fabricated. It did drive choices on splicing these pieces because of their weight and what crane could pick them up and how far you could swing them and handle them. So again, very critical discussion between the engineers and the contractor about how to splice these, where to splice these, such that whatever the pieces were, the modules, if you were something that the contractor could actually handle with the crane in the field. So that drove a lot of the size of these pieces. Ultimately, this is what the outrigger trusses looked like. In Seattle, because we do have seismic considerations to worry about, this gray colored thing here is a buckling restraint brace, whereas this is a double wide flange section right here. So this piece right here acts like a big shock absorber or a fuse in the seismic resistance system. It's designed to yield in an earthquake and have that yield be very controlled. So you can see a little bit of the connections there. It's all pretty huge stuff. And here we are, 10 months to the day. 10 months to the day from the day you saw me looking down out my window, down in the hole, to this day where the proverbial Christmas tree on the last beam goes up to the top. This was actually exactly 10 months to the day that we started, which is pretty miraculous. If you are involved in building buildings of any height, it's pretty miraculous that we got from -7 to level 59 in 10 months. So here's a little video. Hopefully it will run. Yeah, there's a little bit of noise too with it. What we did early days to help our client understand what we were really trying to achieve here is we produced this video. On the left-hand side, you see a sequence of construction where we build a traditional concrete core, traditional below-grade concrete parking garage, and then steel floor framing above. And on the right-hand side was the idea of speed core. How much faster might we go? The original version of this video we produced working with the contractor based on kind of what our best guess was. We thought, well, this is what we think. And so we came up with a story to share with our client that said, we think we can save 6 months. And the client said, wow, 6 months, that's huge, fantastic, proceed. This video that you're watching today, we've now altered, which is actually a record of what we did on the right. So you can see the day counter thing going up in the upper right-hand corner. On the right-hand image, that's actual what we did in terms of the days and the sequence. And what you're going to find here when we're all said and done is that the building on the right was done 10 months before the building on the left. So it was kind of proof that this whole idea worked, and it worked really well. So, of course, Ron, that's all magical, but that's like some animation. Some of y'all are probably from Missouri or something, so here you go. This is for real. We set up a camera on the building across the street and knew somebody was going to be a smartass and say, well, that's a computer animation. Show me the real thing. So here's the real thing. We don't have the sexy music going here, but there you go. And there is a timestamp associated with this particular stream of shots as well. So 10 months from the beginning to the end, really quite miraculous. So since we completed this building, we've now built a second building in San Jose, California, which is a 20-story building, so not quite as tall, only a third the height. But it also saved a number of months on the schedule, and according to the contractor, at least, it saved $10 million in 3 months. This particular project didn't save any construction costs, but it saved 10 months. When you talk to a commercial building developer, 10 months of time is worth tens of millions of dollars. Just the interest on the construction loan itself is $10 million for 10 months. So it's huge, huge dollar savings as well. Anyway, on the left is the architect's rendering. On the right is a real photograph. They look pretty close to the same. So it turned out pretty cool. The building's occupied. It opened about a year ago. And I still live in that white stripy building to the left. Thank you. I'm certain there's a question or two or three, and Dr. Varma will be happy to answer them all. Especially about the equations he presented to you. I know you're all dying to ask about the exponent in the heat transfer equation. Anybody got anything that they want to ask, or are you all stunned? Oh, Dr. Zia, how do you want to do this? You're going to be the mic monitor? All right, like a good student. The young man in the front row.
I'm just curious, architecturally, you have a one side of the building sweeping up. Was that for any reason, for any wind load seismic you put that way, or, well,
so
do you know the...
That's a really interesting question. Let me give you a really complicated answer. The architectural reason that the building sweeps the way it does I don't know if, can we go back? Let me see if I can go back. This isn't that great of a photo for what I'm about to explain. But if you look at the Yamasaki building here, right, it has the pedestal base that is concave here. It was the architect's response to being respectful to Yamasaki by creating a shape that was opposite. That was, and the planning department, the Seattle Planning Department, they loved it because they revere the Yamasaki building. It's a gem of Seattle, and they wanted to make sure that the design of this building somehow respected the 1970s Yamasaki design. So that's why it's that shape. Now, for extra credit bonus points, you would ask, Ron, what engineering challenges might that create? I'm glad you asked that, Dr. Zia. So when you have a building that's this shape, and if you'll remember the core and how the core got smaller and smaller, like a staircase walking one direction, the building wants to lean to the west under its own weight because of the shape and how the gravity load sits there. It wants to lean to the west 8 inches. When we told our client, the building's going to lean to the west 8 inches, how do you feel about that? Hey, what else you got for me? So a whole nother seminar is how we solve that problem. We actually built the building intentionally out of Plum to the east. We gave the contractor, the erector, targets floor by floor by floor. So when they're erecting the steel, they didn't erect it vertically, they erected it tilted to the east. So that over time, and as the weight came on the building, it tilted back to the west. We told them if we do this all perfectly, if we all behave ourselves to the best of our abilities, if we take a plan view of this building and we draw a target around the perimeter 2 inches greater on all sides, if we're inside of that target when we're done, we won. We won. But it wasn't easy. It was very, very challenging when we first described to the contract. It has nothing to do with Speed Core, by the way. It has everything to do with the shape of the building. Last thing on the shape of the building. I know I'm giving you much more than your money's worth. The developer, in their wisdom, when they went to start to design this building, they held an architectural design competition. They had a bunch of different architects draw pretty pictures, and then the owner picked one. He goes, I like that one. You like that one? And they put it on the front page of the Seattle newspaper. Ray Runstead to develop new tower. Here's what it looks like. It's beautiful. And about 3 days later is when my phone rang. And it was the owner of the building, and he says, Ron, we're going to design this building. You saw it in the newspaper. We're ready to go. Let's go. And I said, well, I wish you would have called me before you put it in the newspaper. Because in my college textbook about wind engineering, there's a picture in the book that says, don't do this. It's this building. It's slender. It has sharp corners, and it has a flat top, and it's prismatic. The vortex shedding and the dynamic amplification of the wind that this shape creates is profound. The wind loads for this building were 4 times the earthquake loads. When we made it strong enough for wind, this is the building you want to be in when the earthquake comes. Because when the earthquake comes, this building's elastic. Even in the big earthquake, this building's basically elastic because of the wind demands were so great and as a function of that shape. So a lesson to my client is the next time you host one of these competitions, maybe let me be a judge. Because it cost them a lot of money to solve that problem, but we solved it. Okay, thank you. Who else?
We have a few questions from online, so Shaunik's going to
Yeah, I think we had over 500 people on the Zoom online. So on behalf of all of them, we have one question from them.
One question.
What was the duration from, concept of this to permit drawings, and, what kind of hurdles did y'all face specifically with permitting it?
Yeah, so as Dr. Varma mentioned, this project was subject to a third-party peer review. That peer review group included, I think, 3 or 4. 4. There were 4 members. There was a researcher, 2 practicing engineers, and a seismologist who were part of the review panel. That was paid for by our client, but they worked for the building official. We went through a very rigorous review process. I think from the beginning of the review to the end of the review took about a year. That said, though, it wasn't serial in the sense we didn't do the design and then the year started. How we went about our business is we got through, call it schematic design. We had an idea of what we wanted to realize in our design, and then we engaged this group. So from the moment that we finished schematic design until we got approval, that process was about a year, which in normal sense of designing a building of this scale, that's about normal time, with or without the peer review. So we managed the peer review kind of in parallel with the rest of the design process. It wasn't without a lot of bloodshed. The peer reviewers were really smart. They were very challenging. It was, if you know some of these names, it was Ron Hamburger, chair of ASCE7, Jim Malley, who's a steel wizard design with Degenkolb, Michel Bruneau, who is now on our research team, but then he was the adversary. We had Dr. Varma on our side to counteract Bruneau. And then who was a seismologist, local Seattle guy, C.B. Krause. Anyway, long story short, it was a very rigorous process, but it really didn't take any longer than normal. That's a building like this, to design a building of this scale, a year to a year and a half, depending on how quickly the client makes decisions. That's pretty normal. So yeah, normal. But the tricky part, like I said, was we had enough research to justify that the system worked, but a lot of the details, a lot of the things we thought we might be able to improve upon hadn't yet been completed in research. So we made conservative decisions, like the crosstie example I gave you. The more recent building that we just built, 200 Park, the crossties are spaced at a wider spacing. They're spaced at 18 inches on center, but that was a result of now we had the research in hand to demonstrate that that worked. But in this building, we didn't have that, so we had to make a more conservative choice.
Great. Well, thank you so much. We could give Dr. Varma and Ron another round of applause. And
thank you all. Thank you, Dr. Zia. Thank you.
All right, well, I have just a few notes here. I know I'm standing between you and dinner or the bar, so I'll be quick. But you're here in person today. Thank you for coming. We will have PDH certificates for you at the door. If you are joining us online, those will be emailed to you within the next couple weeks. Let's see. If we could go to the next slide, please. I'm going to introduce the 2023 topic. So we have 2 confirmed speakers for the Allegiant Stadium in Las Vegas. It's the fastest designed and constructed stadium of its size in the U.S. Seats 65,000 people, and it's just a neat project. So we're looking forward to that next fall. So mark your calendars again sometime around this time next year. At this time, we'd like to welcome everyone who's here, any professionals and faculty, to join us for a reception just outside those doors on your way out for food and drinks. And if you have any other questions about the topic, Ron and Amit will be out there. You can bombard them at that point. Anyway, thank you all so much for joining us today, and we look forward to seeing you outside. Have a great evening. Thank you.